Well, welcome to Module 2 of our set of professional development materials to help high school and chemistry teachers incorporate quantum concepts into their classes. This is a module where we finally break into the quantum concepts, and we're going to start with spin. This is a little bit different than how you might have started an undergraduate quantum mechanics class if you took one, because usually those classes start with the wave function, which is kind of the big central mysterious thing in quantum mechanics. But it also turns out that the wave function is very esoteric and challenging to work with mathematically, and actually not necessarily the best place for students to begin with. Instead, we begin with spin, because spin is something that has two options. It can point up or down in terms of its z component. And it turns out this is actually a really good place to start. And so we are, as far as I can tell, the first high school PD opportunity to start with spin 1/2 instead of the wave function. So if anything here doesn't make sense or is too much information, we need to hear feedback about this from teachers, because we want to know if this approach can work in a high school environment. So the first thing we're going to do is talk about why we're interested in spin by looking at a few strange experiments involving electrons and atoms. The first thing we'll ask you to do is watch a couple of videos here. I know you're already watching a video, so there's a video inside the module that we're talking about in this video. But those videos do a great job walking you through these experiments that illustrate that, number one, spin is a thing, and number two, spin behaves really strangely. The next step is for you to try out a spin experiment yourself. So we have here a link to a simulation that will run you through these strange experiments involving spin. It's a pretty straightforward system to use. You have a source here of electrons. I can click and drag that over. You have a detector here. I think they call it an analyzer. And then you have the two outcomes here, these two measurements. What this is going to do when I click start, it's sending basically a randomized beam of electrons down this pathway here. And then it separates those two electron beams along the x-axis, or whatever axis you happen to select here. So we get a measurement along the positive x direction, a measurement along the negative x direction, and I get the collections out here. And what I hope we'll notice is that they're roughly equal. We're favoring positive a little more than negative, but I can always reset and do another trial. If you don't want to wait for the animation, you can also send it forward 10,000 electrons at a time. And when you do that enough times, lo and behold, they're pretty much equal, right? A difference of 26 is nothing out of 15,000. But what you can do with this is change stuff about this. So I can measure the spin along the x, y, or z directions, reset and go with, say, 10,000. And lo and behold, I get very similar results. But another thing I can do, I can add, if I click and drag here, I can add another analyzer. So say I want to go z and then I want to go x. And that's where the interesting stuff happens, because I can add another counter here, reset, and then see what happens when I start examining beams along multiple directions. So this is very straightforward. You literally just click and drag, right click to interact with stuff. There are some instructions here as well. But what you're going to be doing with this setup is following along with 4 key experiments involving electrons and spin. I'm going to let you read that out of the PDF we have here. That's a scan of McIntyre's Quantum Mechanics, so just a few pages out of that walks you through these 4 experiments that we would like you to try out. And then we do have a section here where you can double click and add your answers to these couple questions just about the strange behavior that you see in these experiments. Okay, so now that we've seen that spin is a thing and that it behaves strangely, how do we model this computationally? Well, there's several elements that we need in this model brought up from these experiments that you just completed. We need to be able to specify the probability of measuring the spin up, spin down, spin left, spin right, and spin forward, spin backward along these 3 dimensions. We need to be able to produce the same results on repeated spin measurements, meaning if I do z, 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 I need to get the same results along that. But I also need, if I change up the measurements, if I go z, x, z, I need to reset the spin probabilities going midway through, and I need to account for interference of two separated beams. What I hope to convince you of pretty quickly is that ordinary number scalars will not do for this. I can't simply write down, well, this probability is a half, unless this happened first, in which case it's 100%. Oh, unless this happened in the middle, and then it's back to 50-50. Like, there's not a good mathematical way to do that with ordinary numbers. However, arrays will work. So you might remember in Module 1, where we were learning about Python, we learned how to create arrays. And the idea behind these arrays is that they've got multiple elements. They've got multiple degrees of freedom where I can change the values in these things. It turns out this will work perfectly to describe what's going on in our spin experiments if we start out with two basic arrays, a spin up array and a spin down array. This funny little symbol here with the flat part and the pointy part is called a ket. That name will make sense in a couple minutes. But we represent a ket as an array where one of them has elements 1, 0 and the other one has elements 0, 1. So think of these as regular vectors, right? They have a component here and a component here, and those two components are independent of each other. And so with this setup, I can specify any spin beam just by using these kets. Because if I have one that represents spin up and one that represents spin down, I can get any mixture of spin up and spin down I want just by multiplying each one by a different number, by a coefficient. The idea behind these coefficients is that it's how much of the beam is in the spin up state and how much of the beam is in the spin down state. So for example, if you had a beam that was entirely spin ups and no spin down, you would have C plus equal to 1 and C minus equal to 0. The other extreme, you could have C plus equal to 0 and C minus equal to 1 to have a beam that was entirely spin down and no spin up. And then any mixture is going to be somewhere in between there, right? I could have 50-50, 75%, 25%, etc. Although there's a little bit of some mathematical hoops to jump through to get there. But the way these column vectors work is that you just add the top elements together and add the bottom elements together. So if you take this setup, you're just getting C plus in the top, C minus in the bottom. So it's the spin up coefficient and spin down coefficient. That's pretty much how it works. Now things get interesting here because remember, these coefficients contain the information about the probability for the spin up state and the spin down state. And that's where we need to be able to multiply two different states together. So I need to be able to take one state, say A here, and multiply by another state, say B here. Well, the way I do that in terms of matrices or in terms of arrays, I need to take this column vector, transpose it into a row vector. It also turns out I need to take the complex conjugate, which is why we spent a few minutes on complex conjugate in Module 1. So this section will walk you through some examples of how to do this. What we're going to ask you to do is, can you create a beam that is 100% up and 0% spin down, 2/3 spin up and 1/3 spin down, 10% spin up and 90% spin down? This code is going to take care of that for you because we set up the spin up and spin down arrays here, right? So 1, 0, 0, 1, just exactly like we had above. We're going to check on their inner product because their inner product should be 0 because spin up and spin down should have nothing to do with each other. And then we give an example of a 50-50 beam, but we want you to change these coefficients, C up and C down, in order to get a different beam. We've taken care of everything else. It will calculate the probabilities for you. It will even graph the probabilities as a bar chart here, where you have what percent is spin up and what percent is spin down. So as you play around with these C up and C down values, it's going to change that bar chart to show you the new distribution. So we've learned how to model the actual spin state itself using a 1×2 array, a column vector. What do we need to do then to model the measurement, the actual measuring the value along the x direction, y direction, z direction? It turns out we need to go up one step to a 2×2 array. So a 2×2 array looks something like this, where it's got 4 elements, right? It's got one row and then another row. It multiplies onto the state in a pretty straightforward way. Basically, you take the top 2 elements, multiply them by B1 and B2, and then add the results together. Then to get the next element, you take the bottom 2 elements, multiply by the state elements, and then you get this combination. It's not difficult in terms of the actual math, but it is a lot to have to keep track of, right? That's a lot of coefficients to have to worry about. And so we're going to have Python do this for us. Remember, Python can do this matrix multiplication. So once you and your students get the general idea of how it works, you don't really do this by hand again, right? You put it into Python and have Python do that for you. It gets a little bit more concrete when we take a look at an actual spin measurement. So this SZ here is how you would model measurement along the z-axis, because we've got two possible outcomes. Remember, we've got h bar over 2 and negative h bar over 2. We've got spin up and spin down, and that's what these two diagonal elements represent, is a positive h bar over 2 and a negative h bar over 2. And the action multiplying this onto a state is actually pretty clean. If my state is C plus and C minus, then I take the 1 and 0, multiply them onto here, take the 0 and negative 1, multiply them onto here. Of course, half of these things go away because I've got two zeros in that matrix. So I end up with the C plus and C minus that I started with before. So it looks a little bit like the original state. They're both getting multiplied by h bar over 2, but notice the second one gets multiplied by a negative. So I've taken something that had components C plus and C minus, and now I've turned it into C plus and negative C minus. So I've actually changed the state itself. So this is how you model this weird quantum effect that when you measure something, you change it, right? That's one of the fundamental weirdnesses of quantum mechanics, and it comes here from the way these arrays multiply. So the way we set this up in VPython, we just use an array, right? We just say 1, 0, 0, negative 1, multiplied by h bar over 2. That's exactly what we get here. We're setting h bar equal to 1 just so you don't have a long string of decimals to have to worry about. If you ever want to go use real units, you can just plug in the real h bar there. So what we ask you to try is, again, a few different beams, the same beams that you were using before. So once you figure out what combination will work for C up and C down here, just keep using those in the following sections. So here what we're doing, we're setting up spin up and spin down, the two states. We're setting up the SZ matrix, and you are going to specify C up and C down that you want to try here, based on the states we specify above. And we just want to ask you, what patterns do you notice? Because even though there's a lot going on here, once you get the output, I think you'll notice some patterns going on that happen over and over again. Okay, so the question becomes, how do I start to map this onto an experiment? Because in an experiment, I'm going to have many, many, many electrons flying down this beam, and I'm going to be measuring the average at the end, right? I'm rarely going to measure the spin of a single electron. I'm usually going to measure the average of an entire ensemble of electrons. Well, the way you do that is with one more array multiplication, right? So we learned how to do SZ multiplying onto psi the ket here. Now we need to see how we take psi the bra, the complex transpose here, and multiply that onto SZ and psi. That's a lot to write, so we usually use the shorthand here of just the two brackets on SZ. That just means the same thing here, that this is psi on SZ on psi. And so this condenses down to give you a single number, to give you a scalar, right? Because I have, remember, the SZ times psi gives you a column vector at the end. This bra psi that points the other way gives you a row vector. Row vector times column vector just gives you a single number, gives you a scalar. And so what we're asking you to do is, again, try out several different psis here. This should be pretty familiar because you're always changing this part of the code where you specify C up and C down. We have the expectation value taken care of here because we've got SZ on psi and then the bra psi onto that new ket that you produced there. And then we just ask it to print the expectation value of SZ. Where these expectation values are really useful is we can also calculate the standard deviation. So even though there's all this weird quantum esoteric stuff going on, we're still using average and standard deviation just like you do in lab. When you have your students take many measurements, they give an average and a standard deviation. It's the same thing here. We're just getting it from a model instead of from measurements. The way you get the standard deviation in a measurement, you take that SZ expectation value that you just calculated and you square it. And you subtract that off of this new expectation value. You say, what on earth is going on here? Well, you're multiplying by the SZ twice. Technically, this is SZ squared because you're taking that array, multiplying it by itself. That's another way you can think about it. But the important thing is that this thing is going to have some interesting behavior. So we've got these scenarios here, and we want to ask you, when can you ever get the standard deviation equal to 0? When are you guaranteed to get an exact value of SZ that has no standard deviation? Because it's actually pretty difficult to get. So what we're asking you to do here, again, you're going to play around with the C up and C down. We're also going to ask you to put in the calculation of the expectation value of SZ. That's done above if you go look for it, and then we just need you to square it there to replace those 2 question marks. So the last piece we'll have you take a look at in this module is, where do the challenges come in for students? I mean, you've probably already guessed where some of the roadblocks are, but in terms of the research, there are several points at which students consistently run into issues coming to understand quantum concepts. And they're pretty universal because this is physics going against our everyday human experience and against the physics we've been learning in the classroom. And so it's perfectly reasonable for students to struggle with this, but we want to know where those struggling points are. In particular, students tend to confuse how to calculate a probability with how to calculate an expectation value. How do those differ conceptually? How do they differ procedurally? Similarly, students often confuse the expectation value versus the possible value. So remember, when you measure a spin, you're always measuring spin up or spin down. You're never measuring something in between. But the average can come out somewhere in between based on how many spin ups and how many spin downs you have, even though no individual measurement has the average. Again, that kind of goes back to the lab, right? You might take 20 measurements and get an average that doesn't match with any of the measurements that you actually took. Lastly is this concept of wave function collapse. This is where the state gets replaced by spin up or spin down after you measure SZ. Students have a difficult time making this replacement. I suspect this is actually because there's no mathematical formula to represent this process, but as I understand, there's folks actually working on this in the area of decoherence. So maybe someday in another decade or so, this will become more straightforward for our students because we can give them some mathematical foundation for it. So that's an overview of Module 2. We hope you as a teacher find this useful. We would love your feedback and comments on this module so that we have an idea of what improvements we can make.